In this video, we are going to talk about linear map and matrices, as well as linear operators. This is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and with more examples. The first thing we will talk about is the matrix of a vector. So suppose we have a vector in a vector space. We're going to represent that vector as this column vector, or an n by 1 matrix. This column vector, which I'm just going to say is a vector because it looks just like a regular vector, are the scalars c1, c2 up to cn, such that when you multiply these scalars by the bases vector for the vector space, that'll give you a linear combination for the vector v. And I'm going to use this idea that this is the coordinate vector. In other words, you're familiar with Rn. So if this were, let's say, the vector 1, 2 and R2, you would say that 1 is the first coordinate of our vector and 2 is the second coordinate of our vector. And what that means, this is 1 times our first basis vector plus 2 times our second basis vector, right? So our first basis vector tells us what direction we're in. In this case, it would be the x direction, 1 unit in the x direction. Here we'd have 2 units. We'd use our second basis vector, which is in the y direction, so 2 units in the y direction. So this example you're very familiar with. The thing that will be different then is when we talk about other types of vectors, such as the vector in the polynomial space P3, which is polynomials of degree 3 or less. So we have this polynomial 2 minus 7x plus 5x cubed. If we want the coordinates, we need to write this polynomial in terms of our basis vector. For P3, our basis vectors are 1, x, x squared, and x cubed. So this polynomial here, 2 minus 7x plus 5, 3, is equal to 2 times our first basis vector 1, minus 7 times our second basis vector x, 0 times our second basis vector x squared, and then 5 times our third basis vectors x cubed, which means the coordinates are equal to 2, minus 7, 0, and 5. I also have this comment and picture that comes from our last video, that this m is actually a function, in this example, from the polynomial space into the column vector space. So from P3 of R to R4, or you could say F4. We have this theorem then that relates the matrix of a transformation that we discussed in our last video to this matrix of our bases vector in this matrix we just spoke about. So suppose T is a linear transformation from V to W. V1, V2, Vn is a basis for V, and W1, W2 up to Wm is a basis for W. Then the kth column of our matrix to represent the transformation, denoted mt of dot comma k, equals the matrix transformation or representation of the kth basis vector of V. We will do this example in the main part of our video to illustrate this theorem. We have this theorem that linear maps act like matrix multiplication. In particular, we have this matrix transformation. So suppose T is a linear transformation from V to W, and the vector V is in the vector space V. Suppose V1, V2 up to Vn is a basis for V, and W1, W2 up to Wm is a basis for W. Then M of TV equals M of T times M of V. Our last topic will be about linear operators. So an operator is a linear map from a vector space to itself. So our notation is the script L of V denotes the set of all operators on V. In other words, L of V is equal to the linear operators, the set of linear operators from V to V. And we have this theorem. So remember when we wanted to show that a linear map was a homomorphism or was invertible, we would have to show it was both surjective and injective. If we have an operator, in other words, a linear map from V to itself, then we don't have to do the work of proving both injective or surjective. We could just prove one or the other. and the theorem says suppose V is finite dimensional and T is a linear operator on V, then the following are equivalent. 1, T is invertible, 2, T is injective, and 3, T is surjective. In other words, if you prove just injective, you automatically get surjective, and vice versa. If you prove just surjective, you get automatically injective, and then since you have both, you get invertible. That wraps up our overview, so we'll go back and take a closer look at this matrix of a vector. Looking at the definition of a matrix of a vector, so suppose we have this vector V in our vector space V, and V1, V2 up to Vn is a basis for V, then the matrix of V with respect to this basis, and it's notated with this M of V, is the n by 1 matrix, so it's a column vector. And the m by 1 matrix is C1, C2 up to Cn, where these constants here, these scalars, are the scalars that we need to multiply our basis vector in order to get a linear combination that represents our vector V. As I had mentioned, we're very familiar with this in R2 and R3. The idea that the coordinates, and I'm now going to call this our coordinate vector, 2, 3, and R2 represents, we also sometimes write our vectors this way when in vector calculus, 2, 3, that's 2 in the I direction, the I direction being in the x direction, the positive x direction, and its unit length, plus 3 in the j direction. So this is the I vector, this is the j, if you are familiar with this. And what we do is we scale the I vector by 2 units, the j unit by 3 units, and then the resulting vector is this point here. So actually, this is our vector, 2, 3. But the main idea here is this 2 is multiplied by our first basis vector, and the 3 is multiplied by our second basis vector. So we can also write this as 2, 3 is equal to 2 times E1, our standard basis for R2, plus 3 times E2, our second the second vector in our standard basis for R2, which is equal to 2 times 1, 0, plus 3 times 0, 1. Again, the idea is these coordinates are the coefficients in front of the basis vector. In R3, the coordinates 2, 0, negative 1 would be 2 times our E1 vector plus 0 times our E2 vector minus 1 our E3 vector. And you can see that this linear combination gives us back our vector 2, 0, negative 1. So Rn should be fairly obvious to us, but now we want to figure out the coordinate vector for a polynomial. So we're in the space P3, polynomials of degree 3 or less. We want to find out this matrix of this vector. We start by identifying our bases for P3, which is 1, x squared, and x cubed. And then we can write our polynomial, p of x, as a linear combination of our basis vector. That's going to be 2 times our first basis vector, which is 1, minus 7 times our second basis vector, which is x, plus 0 times our third basis vector, which is x squared, plus 5 times our last basis vector, which is x cubed. So here in blue, I have arrows to our basis vectors, 1, x squared, x cubed, and our coefficients in green, which will become our coordinates, 2, minus 7, 0, and plus 5, which means now our matrix for our polynomial is going to be equal to our coefficients, 2, minus 7, 0, and 5. And one thing to notice is that this matrix depends on the basis of V. So a vector space can have many different bases. Bases aren't necessarily unique. The dimension of the bases is unique, but not the bases. So for a different basis of V, you'll have different coordinates. When we look at this pictorially, we can understand that this matrix then of a vector is a function, it's a mapping that takes a polynomial from P3 and it maps it onto a column vector. The dimension of P3 is equal to 4, so it's going to map it onto a column vector with 4 coordinates. Hence, we have this statement, we want to think of the elements of V as being relabeled into this coordinate vector or this column vector, this n by 1 matrix. And the thing about this mapping is it's an isomorphism. In other words, it's saying that in some sense, the space of polynomials of degree 3 or less is the same as R4. Remember from our last video, we talked about this theorem that said two finite dimensional vector spaces over F are isomorphic if and only if they have the same dimension. And one of the surprising and also very important consequence means that any n-dimensional vector space is isomorphic to Rn and Fn. And that's exactly what this is here. It's showing that M is this mapping, and it's an isomorphism from the space of polynomials of degree 3 or less. It's isomorphic. It's essentially the same as R4. So this mapping here that we've talked about, the matrix of a vector, is exactly the mapping that makes any n-dimensional space isomorphic to Rn and Fn. We're going to take another look at our matrix of a transformation. In particular, we're going to look at the kth column of our matrix of a transformation and find that it's equal to this over here, the matrix of the kth basis vector. So suppose T is a linear transformation from V to W, V1, V2, Vn is a basis for V, and W1, W2, Wm is a basis for W. Then let K be the kth columns, K1, 2, up to N, so as the same dimension as V. Then the kth column of our matrix of our transformation, denoted with the MT, the dot, comma, K subscript, equals M of V of K. And remember, V of K here is one of our bases vector for the vector space V. And I moved this theorem here for your reference. Before we do a proof, I'm going to do a quick example, and I'm going to bring back an example that we did in a previous video. That's the linear transformation from polynomials of degree 3 or less to the space of polynomial of degree 2 or less. And our transformation was D for differentiation. So D of P of X is equal to P prime of X. And we found the matrix D with respect to the standard bases. So the first thing I'm going to do is write my standard bases for P3, which is 1x, x squared, x cubed, and my standard bases for P2, which is 1x, x squared. Now I want to build up my matrix for my transformation D, column by column. That's what this dot comma K equals. And what it says is that's going to be equal to the matrix representation of the kth bases vector written in terms of P2. In other words, in a previous video, one of the things we said is when we have a transformation from a space, in this case P3 to P2, we can simply find out what the transformation does to the bases vectors of P3, and then we will know how all vectors are transformed. And that's because any polynomial of degree 3 or less is of this form, the a0 plus a1x plus a2x squared plus a3x cubed, and any transformation, in this case we're talking about the derivative, but any transformation of this vector can be broken down, because it's linear, into a0 times the transformation on the first basis vector, which is 1, plus a1 times the transformation on x, plus a2 times the transformation on x squared, plus a3 times the transformation of x cubed. So again, once we know how a transformation affects the basis vector, in this case it's 1x, x squared, x cubed, we can figure out what happens to any vector in the space. So for this example, I'm going to take my transformation on my first basis vector. My first basis vector is 1. So the derivative of 1 is equal to 0. Now I need to write this 0 in terms of my bases in P2. So that's going to be 0 times 1 plus 0 times x plus 0 times x squared. Now writing it here as the matrix of this vector, the coefficients are 0, 0, 0. So my matrix representation of this vector is going to be 0, 0, 0. And I'll just note that that's M of V1, my first basis vector. For my second basis vector, that's x. So d of x, the derivative of x is equal to 1. In terms of my bases now, I've moved from P of 3, I've taken the derivative, so now I'm in P2. So in terms of my bases vector, that's 1 times 1, 0 times x, and 0 times x squared. As a matrix, that's going to be, the coefficients are 1, 0, 0. That's 1, 0, 0. That's the matrix of V2. For my third bases vector, that's x2, the derivative of x2 is equal to 2x. Now, again, we've taken the derivative, so we've moved over to our new space, which is P2. So writing 2x as a linear combination in our new bases, that's 0 times 1, 2 times x, and 0 times x squared. So our coefficients are 0, 2, 0. This is our coefficient vector, which is MV3. And then finally, I'm going to take our derivative of our third bases vector, x cubed, which is 3x squared. Again, writing it in terms of our P2 bases, that's 0 times 1 plus 0 times x plus 3 times x squared. So our coefficients are 0, 0, 3. Our matrix then for V4 is 0, 0, 3. According to our theorem here then, the kth column of our matrix that represents our transformation is going to be the transformation on our kth bases vector. So let me write that down here. Then our first column of our matrix of our transformation is going to be the transformation on our first vector. The second column is the transformation on our second vector. The third column is transformation on our third vector. And the fourth column is the transformation on our fourth column. And that gives us this matrix here. So we take this column, 0, 0, 0, this column, 1, 0, 0, this column, 0, 2, 0, and our last column, 0, 0, 3. This is our matrix that represents this derivative transformation. To illustrate how this matrix of a transformation works, let's say we have a polynomial in P3. So let's say our polynomial is equal to 6 plus 2x plus 0x squared plus 4x cubed. Our derivative then would be equal to 2 plus 12x squared. What we can do now is take our matrix of our transformation, which is column vector 0, 0, 0, 1, 0, 0, 0, 2, 0, and 0, 0, 3. We can multiply now by the vector that represents this starting polynomial, and the vector is going to be 6, 2, 0, 4 over here. When we do the matrix multiplication, this row times this column will give us 2 for our first coordinate. This second row times our column will give us 0 for our second coordinate, and this row, the third row times our vector, will give us 12 as our last coordinate. So this is the vector represented in P2 now, because we've done the transformation. So this vector, rewriting it in terms of a polynomial, these are our coefficients. That's 2 times 1, 0 times our second basis vector, which is x, and then 12 times our second basis vector, which is x squared. So you can see we get 2 plus 12x squared, which is the same thing we had when we took the derivative the old-fashioned way. I've taken another example from one of our previous videos. This one I don't think is as interesting because it's just going from F2 to F3. It's not some interestingly different vector space from Rn like the polynomials, the space of polynomials or the space of functions, but this is a quick example. So to go from F2 to F3, we have this transformation that takes xy and it maps it to x plus 3y for the first coordinate, 2x plus 5y for the second coordinate, and 7x plus 9y for the last and third coordinate. We have our basis for F2 is 1, 0, 0, 1, and our basis for F3 is E1, E2, E3. So now to find our matrix for our transformation, we're going to do the transformation on our basis for F2. So I have T of our first basis vector, 1, 0. I'm going to plug that into here. I'm going to have 1 plus 3 times 0, 2 times 1 plus 5 times 0, and 7 times 1 plus 9 times 0. So I get the vector 1, 2, 7. And again, this is M of V1, 1, 2, 7. Taking our transformation on our second basis vector, 0, 1, I'm going to get 0 plus 3 times 1, 2 times 0 plus 5 times 1, 7 times 0 plus 9 times 1, which is the vector 3, 5, 9. So m of our second basis vector is 3, 5, 9. That means our matrix now is going to be 1, 2, 7 for our first column and 3, 5, 9 for our second column. Again, this is the matrix that talks about how our basis from F2 is transformed to F3. So to show how this matrix works, let's say I wanted to do my transformation. This shouldn't be an F, but it should be a T. If I want to do my transformation now on the vector 2, negative 1, I can plug it straight in here, and I get 2 plus 3 times negative 1. I get 2 times 2 plus 5 times negative 1, and 7 times 2 plus 9 times negative 1, which is negative 1, 5. Or I can take my matrix of transformation 1, 2, 7, 3, 5, 9, multiply by my vector in R2, 2, negative 1, and I will get the same vector negative 1, 5. At this point, we've covered this theorem here. We've covered our example with our polynomials. We also have one more theorem. Linear maps act like matrix multiplication. So we'll suppose T is a linear transformation from V to W, and V is a vector in the vector space V. Suppose V1, V2 up to Vn is a basis for V, and W1, W2 up to Wm is a basis for W. Then M of the transformation of V is equal to M of T plus M of V. Our next topic will be on operators. And I moved my definition over here to give me some space. So we denote this, the script L of V. An operator is a linear map from a vector space to itself. So L of V denotes the set of all operators on V. In other words, L of V is equal to the set of linear transformations from V onto V. Next, we have this theorem about operators, but so that you understand the significance, I want to remind you about this theorem we had from our last video that said a linear map T going from V to W is invertible if and only if it is injective and surjective. So in order to prove a linear map T was invertible, we had to show two things, injective and surjective. Now for an operator, when T goes from V to V, so T is a linear operator on V, then the following are equivalent. T is invertible, T is injective, and T is surjective. So now, if you want to show T is invertible, you only have to show one or the other, injectivity or surjectivity, because T is injective automatically gives you T is surjective, which means you automatically get invertible. Or, again, if you want to show it's invertible, if you can show it's surjective, you automatically get injective, which means you automatically get invertible. To prove this theorem, instead of showing that T is invertible implies injective, and T is invertible implies surjective, and T injective implies invertible, and T injective implies surjective, and T surjective implies invertible, and T surjective implies injective, which is like 2, 4, 6 things to prove, we're going to prove 4 things. We're going to prove that T invertible implies T injective, which implies T surjective, which comes back around and implies T invertible. So this is the little loop. Invertible implies injective, implies surjective, implies invertible. So we have our 3 parts of our proof. We're going to start with invertible implies injective. And this first one is kind of easy because invertible automatically implies injective and surjective, right, from our theorem from our last video. So we get this one pretty easily. Now we want injective implies surjective. This is new. We have this theorem from our last video that says injectivity is equivalent to the null space equaling 0. So since we have injectivity, that means our null space is equal to the 0 vector. We have the fundamental theorem of linear maps that says suppose V is finite dimensional and T is in the space of linear maps from V to W, then the range of T is finite dimensional and dimension of V is equal dimension of null of T plus dimension range of T. So I'm just going to write that out. Dimension of V equals dimension null of T plus dimension range. Since the null of T is equal to the 0 vector, remember this is a single point, the dimension of the 0 vector is equal to 0. So we have the dimension of V is equal to dimension of range. Since their dimensions are equal, remember we have that theorem, that means one space is just an isomorphism of the other. In other words, the range of T is equal to V, which implies that this operator is surjective. Finally, we have surjective implies invertible. And we're going to need more space for this proof. It's not difficult, very similar to this one here, but we definitely need more space. So proving surjective implies invertible, we'll start with surjective implies that the range of T is equal to the entire space V. Again, we're going to use the fundamental theorem of linear maps. We're going to suppose V is finite dimensional. I'm just going to skip to here. Then dimension of V is equal to dimension of nullity plus dimension range of T. So writing that out, dimension of V is equal to dimension nullity plus dimension range of T. Now here we said, because it's surjective, the range of T is equal to V. So rewriting this, dimension of V equals dimension null of T. Now we can substitute dimension of V again, which means when we subtract dimension V from both sides of the equation, we have 0 is equal to dimension of null of T. Using this theorem again, injectivity is equivalent to the null space equaling 0, and here we have the dimension of null of T is equal to 0. That can only happen when null of T is equal to the 0 vector, which has dimension 0. So what we are saying then is, since the null of T is equal to the 0 vector, by this theorem here, that means T is injective. Also, we started out with the assumption that T is surjective, which by definition of invertible means that T is an invertible map. We will illustrate use of this theorem here with the example, show for each polynomial q of x in the space of polynomial, there exists a polynomial p in the space of polynomials, such that if we multiply p times x squared plus 5x plus 7 and then take the second derivative, we will get q of x. The first thing to note is we cannot apply this theorem here to p of r because our general space of polynomials of an infinite, possibly infinite dimension does not apply here because v needs to be finite dimensional. But we can apply the theorem to Pm of r, in other words, polynomial of degree m or less. So instead of letting q just be a polynomial, we're going to say let q be a polynomial of degree m or less, and then we have this transformation from Pm to Pm such that t of p of x is equal to p of x times x squared plus 5x plus 7, this product then double primed. And just a quick note, this product is in p of m, in the space of polynomials of degree m or less, since when we multiply p of x by x squared plus 5x plus 7, we're going to increase the degree of the polynomial by 2, but then by taking the derivative twice, we're going to decrease the degree by 2, so we're left back at p of m. If we now want to show t is invertible, because it is a linear operator, in other words, our w is equal to our v, or it maps onto itself, we can choose to either show t is injective or t is surjective. We don't need to show both. I'm going to focus on t being injective. So to show t is invertible, we'll look at injectivity. And to do this, we're going to consider the null of t. And these are polynomials p of x such that when we multiply by x squared plus 5x plus 7, and then take the second derivative, it will equal to 0. But we also know the polynomials q of x, where q double prime of x is equal to 0, are of the form ax plus b, right? So if we take the first derivative of ax plus b, we're going to get back a, and then when we take the second derivative, we will get back 0. But we can have an x term, we can have a constant term, but we cannot have a squared term because it will not equal 0 unless x is equal to 0. But looking here at p of x, since we have this squared term multiplying by another polynomial, there's no way we're going to get rid of that squared term. So this polynomial, p of x times x squared plus 5x plus 7, has degree of at least 2. And it's not of this linear ax plus b form. So in other words, the only way that this can give you a 0 after the second derivative is if p of x is equal to 0, which means that the null of t is equal to the 0 vector. We've seen this theorem before. In fact, I didn't even finish writing it all out, but injectivity is equivalent to the null space equaling the 0 vector. So what we have shown then is t is injective. And previously we showed that t injective implies t is surjective, which means now that t is invertible. Before we do our review, I do want to mention operators are special cases of linear maps, and there will be another video or two that focuses on operators, so you want to be sure that you know it's just for operators and not for linear maps in general. That's a very important distinction to make. Okay, to review what we've gone over in this video, first we talked about the matrix of a vector. So suppose V is a vector in the vector space V. Then the matrix of the vector V with respect to a basis for V is the n by 1 matrix, or this column vector, of coefficients c1, c2 up to cn, where c1, c2 up to cn are scalars, such that when you multiply them times your basis vector, that linear combination will equal to your vector v. In other books, this column vector is called the coordinate vector, and I often use the term coordinates. And you will notice that the matrix vector depends on the basis of V, because the vector space V could have many bases. So it's important that your coordinate vector, you know what basis you're discussing. We did this example here where we had a polynomial of degree 3 or less, which was 2 minus 7x plus 5x cubed. Writing this in terms of the bases for P3, we have 2 times 1 minus 7 times x, 0 times x squared, and 5 times x3. Now taking the coefficients, or the scalars, 2 minus 7, 0, and 5, that will then give us our matrix of the vector 2 minus 7x plus 5x cubed. And we have this picture to remind us that in this example, our mapping takes a vector in P3, which is dimension 4, and maps it to a vector of R4. We talked about how we can link this definition of matrix of a vector, when we have basis vectors, to the matrix that represents a transformation. And we said the kth column of this matrix of a transformation is simply the matrix of the kth basis vector after the transformation. And we did this example here with the polynomials in the main part of our video. We're not going to do it again in the review. We had this theorem that said linear maps act like matrix multiplication. And then finally, we discussed operators, which is a linear map from a vector space onto itself. In other words, L of V is equal to the set of linear maps from V to V. And finally, we had this theorem for operators. So suppose V is finite dimensional and T is a linear operator on V. Then the following are equivalent: T is invertible, T is injective, and T is surjective. And that's it for this video. Thank you for watching.